Hello, this is Team 13's Lab 5 final demo video presentation on color organization with the 4 degree of freedom arm. Lab 13 is comprised of Elowen Eckers, Alice Graham, and I, Kylie Welcher. The creation of this OMX robotics manipulator truly began with the definite Hartenberg parameters. This follows the steps of assigning the z-axis of each joint in the direction of positive rotation through the right-hand rule of for a rotational joint. Using these axes, we find the common normal between each one, and then define the y-axis through the right-hand rule. Using these axis definitions and measured lengths, we could fill a DH table. We plug these values into a homogeneous transformation matrix for each transformation from joint to joint. Doing matrix multiplication for each transformation matrix, create a final transformation matrix from the frame 0 to the frame of the end effector. We use MATLAB function and Sims to symbolically solve our transformation matrix for any given angle, allowing us to achieve forward kinematics. Next, we use geometric analysis to create inverse kinematics, using basic trig analysis. Because the number of joints on an arm is greater than the number of dimensions in task space, we decouple the end effector and the fourth joint from the rest of the arm. We also use Sims to solve these equations for any given task space value. We then moved on to trajectory generations. We use the quintic and cubic matrix forms of each generation with matrix division to find the transformation coefficients and function for a given trajectory. This allows us to calculate the position of the end effector for a given time. We use these functions to generate the task space values for a point along trajectory and use tick and talk to move along this trajectory. From the graph, you can see the benefits of quintic trajectories as we control acceleration, limiting jerk of the robot. From these diagrams, you can also see the difference between mapping from joint to task space, for kinematics, on the left, and task to joint, inverse kinematics, on the right. For Lab 4, we explore the Jacobian and velocity kinematics of the arm. Differential kinematics addresses the issue of complicated equations from the DH table by introducing the Jacobian matrix, which maps joint velocities to linear angular velocities of the end effector. Using our DH table, we found the transformation matrix from each joint I from frame 0, and followed the formula to calculate Jacobian, which is made up of the Jacobian of joint 1 all the way to joint 4. We used another MATLAB function to achieve a symbolic Jacobian, and then we got a final Jacobian from T0 to 5. Next, we looked into singularities. We used the determinant of J times J transport, because you need a squared matrix to find a determinant. As the determinant gets closer to 0, the Jacobian gets less and less invertible, meaning it's losing a degree of freedom, meaning we are reaching a singularity. We also use the differential kinematics to analyze the real versus goal velocity of the end effector. Finally, we got our camera involved. We used the MATLAB camera calibrator to calibrate the intrinsics of the camera by taking multiple flows from different angles of the checkerboard. We analyzed the histogram to determine if the reprojection error, the distance between the checkerboard points detected in the calibration image and the corresponding world points projected using the estimate camera matrix, was small enough. We want the error to be below 1 pixel. Next, we went to extrinsic calibration, which transformed the image frame to the checkerboard frame to robot frame via inspection from robot base frame to the checkerboard frame and point to world, which is a given MATLAB function, which took us from image to checkerboard frame. Next, we took more photos to the color calibrator camera and generate color masks. First, we masked and undistorted the workspace, the checkerboard, by using values of the outermost corners of the checkerboard. Then we used the color threshold map. We chose the HSV color model for color recognition/segmentation because it aligns more closely with human perception of color and generate less fuzzy or noisy masks because distinct colors are more easily separable by it. MATLAB then generated masks for each of these colors. We would use these masks to find blobs of each color, and then we'd find the centroid of these blobs, or ball, to figure out where we should move our arm to. But because the camera is mounted at an angle, we had to correct this found XY location to the actual XY coordination in the frame of the robot through geometry. After all that math analysis, we used blocking code, trajectory generation, and other things we coded before in other labs to actually find, sort, pick up, and place balls. This is the end of our final video. Thank you for watching.